Hi everyone, my name is Zhishan Guo from University of Central Florida. Today I'm going to present a paper about the safe and effective application of probabilistic techniques in safety critical systems. The other co-authors are Professor Kuna Agro and Professor Sanjoy Barua from Washington University in St. Louis and Professor Jing Li from NJIT. So cyber-physical systems can be viewed as contains the following three components: the software, which executes on some computing platform, and both will interact with the outside environment via sensors and actuators. Many ideas have been integrating probabilistic concepts into the system's analysis and design, advocate for the modeling of the lower two components via probabilistic models, such as probabilistic timing profiles, stochastic arrival patterns, and so on. However, this paper proposes something different, that we want to apply probabilistic approach or randomization into the software only, or the algorithm side for safety critical systems, while the models of the other parts are continued to be assumed with the worst case ones. Our claim is that randomization and randomized algorithms can indeed be used in safety critical cyber-physical systems design, where probabilistic guarantees can be provided using the concept of concentration bound, and which is probabilistic bound on the likelihood of the performance of a randomized algorithm deviating from its expected performance. And these are well compliant with the safety standards, such as IEC 61508, as suggested listed below. So we want to make a little clarification of the context. First, as we mentioned, that cyber-physical systems can be seen as the following three components, while here in this paper, worst-case models are considered for the environment, for the execution on the platform, such as execution time, and also the interaction with the environment, such as your arrival pattern, the period. The randomization is considered only at the software level, such as the task schedulers or resource allocation mechanisms. So we will view three examples of how such randomization can be applied to the software side of cyber-physical systems. First, let's take a small and well-known example to start with, which is quicksort. So we know that in quicksort, a pivot element is chosen, and the whole array is separated into three subarrays. The ones that are larger than the pivot, smaller than the pivot, and also equal to the pivot. Then it's a recursion process that will perform quicksort again on the subarrays. Our focus here is, of course, the analysis, and where we care about the number of total comparisons that are needed for quicksort. And we all know that in the worst case, quicksort runs in the number of comparison is order of n squared. And this happens when the pivot is always the worst element. So for example, if an array has 100 elements, then the worst case comparison is about 5,000. However, what happens if we choose the pivot in a randomized manner? Then another well-known result that is that the expected number of comparisons will be order of n log n, which is much smaller than n squared, as we all know. So here it's about 600 something comparisons. However, this is only the expected number of comparisons. What happens to the worst case? Well, what we need for safety critical systems are guarantees. However, it may not be the absolute worst case. So let's look at the probability of how likely will the number of comparisons exceed a certain value that's greater than the expected value, but not as large as the worst case. So with the theoretical result that we call concentration bound for quicksort, we know that the probability of number of comparisons exceeding the expected value by a certain ratio is not so large. It's order of log n. So basically, it decreases exponentially with an increasing epsilon. And so here, without focusing on the details, we did some quick calculation to demonstrate how good this result is. That according to different security or certification levels, you may allow different probabilities of failures, either per hour or per occurrence. And the corresponding number of comparisons, upper bound of number of comparisons, with respect to the concentration bound we just seen in the last page, are the followings. As you can see that even with the very high certification level of probability of 10⁻⁴, it's just about 1,000 comparisons, which is not so great compared to the expected value for n log n case, and much, much smaller than the actual worst case of the n squared case. So if we were to use quicksort in part of the safety critical systems design, and for example, this has to meet certification level of SEL3, then we could assign 966 comparisons, whatever execution time that such number of comparisons will take as the worst case, and that will comply with level 3 of certification requirement. So now let's look at another example called buffer sizing. So where you are given a processing node and n buffers, which holds n incoming flows, and a total amount of at most 1 unit of flow across all the buffers. So each may have a fraction of this flow, but they sum up to 1 per unit time will arrive. So every time unit, there will be multiple flows that sum up to 1 that arrives into all these buffers. At each time unit, this processing node is allowed to process up to 1 unit of flow at a time, but you can only take from 1 of these buffers. So basically, if you assign multiple ones, then you can only take from 1 of it and execute up to 1 unit of flow. So apparently, some other units, fractional units, will be left over in the other buffers. So slowly they will accumulate unless you took a unit from that buffer later on. So the question is, what is the required buffer size so that we don't lose any of the information inside this flow? So this problem is identical to finding the maximum backlog that can build up in any buffer. And certainly one can simply consider a greedy strategy that you always take a unit of flow from the largest, the one with the buffer with the largest backlog. And this greedy approach leads to a log n size, order of log n size bound on the backlog. And actually, theoretically, it has theoretically been shown that no deterministic algorithm can guarantee asymptotically better backlog. What about randomized approach? Actually, they can achieve a smaller expected backlog, which is of order of log n. Note that this is exponentially better as opposed to the order of log n backlog of determinism algorithms. And here is the concentration bound result that are derived by existing existing paper. So basically, this gives the probability of the backlog exceeding a certain value k. And note that this does not really depend on how many backlog you have, how many buffers you have. So this is quite scalable. So one last example we want to show is in multi-core scheduling of directed acyclic graphs in real-time systems. And this is considered as one of the most advanced and representative workload model for today's real-time embedded systems. And this is actually quite similar to the makespan minimization problem in traditional scheduling theory, which is a well-known NP-hard problem. So a greedy algorithm can construct a work-conserving schedule, which is called the Graham's list scheduling algorithm, where at each time instant, you schedule a job that if it is available upon any available core. And we know that this algorithm is about has a competitive ratio of 2 minus 1 over m, where m is the number of cores. So basically, if this greedy approach, if there's an optimal approach that can achieve a makespan of SOPT, which stands for optimal, then this greedy approach will achieve a makespan no larger than this. So basically, it's too competitive. And we know that determining a schedule for a DAG with makespan smaller than 4/3 of the optimal schedule is a NP-hard in the strong sense problem. Basically, you will even have pseudo-polynomial time solutions. Okay, so this is a quite nice theoretical result and performance, but there are implementation issues. First, when your number of processors becomes large, which is the current trend for multiprocessors platforms, you may have a very large queue, which is the bottleneck. And so we want to use distributed queue to remove this issue. So why don't we assign each processor a queue? Then you have the second implementation issue, that some cores may be idle, while some other cores may have a very full queue of workloads. So these queues of execution requirements may not be that well balanced because it's distributed. So here, one way to handle such imbalance issues for the queues is work stealing. You can steal, each processor can steal a job from the first non-empty queue. Okay, so this is a greedy work stealing strategy that if you are empty while others are busy, you just steal a job from the other queues if it's not empty. And there are drawbacks of this greedy approach, that in the worst case scenario, still a single queue will be overloaded, and while others are kind of empty. So the performance becomes very similar to a centralized queue. And again, randomization can help here. So this is the upper bound on the makespan using greedy list scheduling for a centralized queue. Okay, so this is at as least, and here L is the maximum cumulative execution time of any sequence of a DAG, while W is the cumulative worst case execution time of all the jobs. It's the work. So what happens if we use a randomized work stealing scheduler on a distributed queue? Now, actually, it has been shown by our earlier work that the expectation of the makespan for this randomized work stealing scheduler will achieve a not so bad bound, where you see that the workload, this part is the same as the greedy approach, but this part is just a constant, which is phi, big phi, about 3.65. So this indeed will be slightly larger than the S list, because we are using, remember that we are using a distributed queue. And the corresponding concentration bound is denoted as the following inequality. So basically, this is the middle part is the expectation of the make span. While if you want a small probability, you just add a little bit, which is a log of 1 over epsilon, which is a relatively small value over the expected value. So basically, this distribution or this likelihood has a very small variation, so that it's relatively cheap to achieve a small probability of the workload, make span exceeding that larger bound, a slightly larger bound. Okay, so we experimentally verified this result using some benchmark programs written by Silk Plus with the randomized work stealing approach. And these are the following benchmarks. And here are one of the experimental results, where on the x-axis, we have the number of cores, while on the y-axis, we have the make span. And the this dot here means that for 8-core processor, the concentration bound that we calculated according to the previous expression is about 8 seconds, while the actual distribution, where we use a box plot here, has an average of about 5.5 seconds for the make span. And this standard deviation is so small such that you cannot actually see the box. It merges there. Okay, and these are for all the 6 benchmarks. They all have similar trajectories, where we can see that the distribution of the actual observations of at least 100 run per setting all follows very closely to the average case, and the derived concentration bound on the probabilities are way larger than the actual observed case and remains very safe. And actually, in all these runs, none actually measured a make span that exceeds the concentration bound. So to summarize, we have proposed an approach for incorporating probabilistic and statistical techniques in safety critical applications, and this is called concentration bound. And we only randomized algorithms for which good concentration bound is known are used. Since safety standards allows non-zero failure probabilities, this proposed approach remains compliant. And for future works, we want to identify more randomized algorithms that can enhance the resource efficiency for safety critical systems. And of course, we need to derive the corresponding concentration bound for these algorithms. Okay, so thank you very much for your attention. And I look forward to handle any questions you may have at the live session. Thank you.